In 1953, television writer Leonard Stern was stuck on an adjective for a script. His friend Roger Price walked in, and before Stern could even finish his sentence, Price threw out two words, clumsy and naked. They laughed, realized they had stumbled onto a functional linguistic structure, and eventually named it Mad Libs. The mechanics use a template where each blank demands a specific word type, a noun, a verb, an adjective. The comedy comes from semantic mismatch. The person provides correct input, a noun for a noun, but has no contextual awareness of the surrounding sentence. This mirrors the logic your code becomes before executing, an abstract syntax tree, mapping the machine's instructions. Writing Python means providing words to fill this tree. One node expects an expression, another an identifier. The interpreter then fills invisible C templates, cascading into assembly. But templates require a place to store the words they use. In traditional programming, we keep the storage and the templates in two different worlds. In AI, those worlds have finally collided. Traditional computer memory operates as a strict hierarchy, built to balance processing speed against total storage capacity. At the top, closest to the CPU, you have registers and cache. These are tiny, expensive, and incredibly fast, holding only the data the machine thinks it will need in the next few clock cycles. Further down the chain is the main RAM, and eventually the massive, slow archival storage, solid-state drives, spinning magnetic platters, or the reels of tape found in cold storage. The absolute rule of this architecture is the hard boundary between code and data. The instructions that tell the machine what to do are kept strictly separate from the information the machine operates on. This separation is a primary security defense. In a buffer overflow attack, the goal is to trick the machine into treating data as code, which allows the machine to be hijacked by its own inputs. Maintaining this wall has been the unbreakable law of computing safety for 70 years. Now, artificial intelligence is removing the wall entirely. AI memory has its own hierarchy. It starts with model weights, fixed knowledge encoded during training that acts as the model's unchangeable long-term memory. Then there is the context window. This is the temporary working memory that holds everything relevant to a single interaction, from your conversation history to any documents you've uploaded. Inside that window sits the system prompt, which acts like firmware. It sets the operating parameters, telling the model who it is, what it should do, and what constraints it must follow. Here, the sacred wall disappears. The system prompt is not compiled separately from the user's message. Everything is flattened into a single stream of text tokens, and every token is processed identically. This allows for prompt injection. If a user inputs the phrase, "ignore your previous instructions," those words are fed into the same pathway as the core system rules. The model reads the injection exactly the same way it reads its own firmware. By treating instructions and information as the same medium, the architecture lacks a native way to distinguish between a command and a conversation. Many argue that this lack of separation makes AI far too probabilistic and unreliable to ever be trusted with real engineering work. In 1952, Grace Hopper faced this same skepticism when she built the first working compiler. The experts of her era told her it was impossible because computers could only perform arithmetic, not process language. They viewed the abstraction of a compiler as a source of unreliability. They believed that moving away from direct machine code would introduce errors that couldn't be controlled. But the truth is, every layer of computing is built on uncertainty. At the lowest level, electrons moving through a transistor are probabilistic quantum particles. They don't even have definite positions until they are measured. We made these unpredictable particles reliable through decades of architecture and error correction. We built redundancy and logic gates specifically to handle the physical failures we couldn't prevent, forcing a probabilistic system to behave deterministically. Prompting is the newest, highest abstraction layer on top of that stack. It replaces the rigid syntax of code with the meaning and context of natural language. Because a wrong word in this system results in a jailbreak rather than a Mad Libs joke, we have to stop treating prompts like conversational tips. The path forward is what has always been, building the engineering infrastructure that turns an unreliable layer